Hello, this is video number 24. While you weren't looking, I went ahead and wrote a truth table on the board. This, I don't know, maybe this has some special logical function, but as far as I'm concerned, it's just a random digital logic function. We've got the all of the input rows over here listed in canonical order, 0, 0, 0 through 1, 1, 1. And then our output function, just generically, I called it F1 for function 1. 0, 1, 0, 1, 0, 1, 1, 1. Can we write an SOP for that? Yeah, we know how to do that now. Sum of products, canonical sum of products. We put what expression we need to generate each one of the ones and then OR them all together. We'll see this one, specifically this one, if A is off, B is off, C is on. A is off, B is off, C is on. And. How else can we see a 1? We can see a 1 if A is off, B and C are both on. A is off, B and C are both on. How else? How about A on, B off, C on? So all of them are on except for B. So A, B off, C. Or, how far did I get? Right here. A and B are on, C is off. A and B are on, and C is off. And all three of them are on, A, B, C. So you could view that as a little bit of a review. Even if you don't know what this is, you can still figure out what the canonical sum of products is by just figuring out how to generate each of these ones logically. And a parity check, I should have 1, 2, 3, 4, 5 products. 1, 2, 3, 4, 5, and in fact I do. Canonical is the right order, but it sounds like canonical, well, that must be the best. That's the gold standard. Except what we're about to find out is, in some ways it might not necessarily be the best. Let's do a shopping list if we're going to actually build this circuit here. List of gates that we'll need. Well, A, B, and C at one point or another, they're all knotted, so we're going to need 3 NOT gates. That's almost always going to be the case in a non-trivial circuit, but 3 NOT gates, knots. How many ands? 1, 2, 3, 4, 5 ands, 5 three-way ands, and an OR gate, a big wide OR gate. 1, 2, 3, 4, 5. 1 5-way OR gate. Okay, there we have it. A recipe. Now all we've got to do is fire up logically. I'm just going to start calling it logically. You know what I'm talking about. Fire up the logically program. And away we go. And there's our recipe for implementing the circuit. So what could I possibly want to write down here? I'm going to make an observation, OBSV. Or actually perhaps try to lead you into making an observation. Look at the last 2 products in our SOP. Look at the, at spelled with a T, at the last 2 products. And it goes without saying that I mean products in the SOP, but there it is. And here's a weird one. I'll just phrase this as a question. What do they tell us? What a weird question, yeah. What do they tell us? I suppose if you could read my mind, you know what I'm talking about, but that's going to be the only way. I'm going to highlight these. Here are the last 2 products right here. A and B and not C. A and B and C. They have some stuff in common, don't they? Actually, they do. What they're trying to tell us, even if we will listen, is that if A and B are both on, then C doesn't matter. Let me write that down with an open marker. What do they tell us? if A and B are both on, but in terms of the truth table and in our circuit, on means 1. If A and B are both 1s, drum roll, then the value of C doesn't matter. If you could visualize light switches in the logically program, see, I didn't stop and call it logic.ly. I'll try not to do that anymore. In our logically program, if we've got our little light switches set so that A is on, B is on, they're both 1s, then bless its heart, little c can flip back and forth like there's no tomorrow, and it's not going to change the output. We're going to see a 1 if A is 1 and B is 1, regardless of what the switch setting is for C. That's exactly what I just got through saying just a second ago. I guess I'm saying it again to help it soak in, just for emphasis. So, that's the next question. So what? What kind of an observation is that? That's not useful. Oh, yes, it is. Oh, yes, it is. So the last two products can be replaced by A dot B. And that's such a big deal, I'm going to put a pink box around that. What we're looking for is a formula to realize or to implement this logic circuit here, this logic design. And stage 1, of course, is to get the truth table. Somehow or other that has to be generated. And then from that, we get the SOP. And then from the SOP, what we've been doing is going directly to the logically programmed. See, I said it without the dot. Stop mentioning the dot. We go directly from this to logically and implement this as a circuit. And here's what we would need. Two of the three-way AND gates that we need are just for this part of the SOP. We would need a three-way AND for that, a three-way AND for that, and the bigger OR. If we rip this out, pretend like that's the entire formula there. If that's the entire formula, then that's two three-way AND gates and a NOT gate and an OR gate. Look at this. One dinky little two-way AND gate, and that's it. And this has the entire logical expressivity of that. This pink bracketed thing does exactly the same thing as that little pink box thing. Which says to us, if we will listen, it says to us, we don't have to implement all of that. There are ways to simplify this down, boil this down, using exactly this sorts of observation here. That if some things are set, then other things don't matter. What we're going to end up with is not going to be a canonical SOP, it's a reduced SOP. But it's going to give us less stuff that we have to shop for. We'll be able to implement it with fewer gates, it takes less time, it's more efficient, it'll run faster, all those good things. And I filled up the board completely. You know what? To give me time to erase it, commit all this to permanent memory. Burn it into your memory, and I'll be right back. Until then, I'll see you online.